Hi, this talk will be about our explicit constructions of extremely depth robust graphs. Let's begin with the definition of a depth robust graph. Intuitively, a directed acyclic graph G is depth robust if, even after deleting many nodes, the remaining graph still has a long path. Formally, we say that a det G is ED depth robust if, for any subset S of size E, the det G minus S still contains a directed path of length D. We want to achieve the following properties for the depth robust graphs, such as large E and D, small in degree, and local navigability, which means that we can efficiently find all the parents of a given node V. Depth robust graphs have many applications in cryptography, such as data-independent memory-hard functions, proofs of space and replication, proofs of sequential work, and more. We remark that some of these applications further rely on a stronger notion called epsilon extreme depth robustness. As you can see in the table, there are several prior constructions of depth robust graphs. Here, I would like to just emphasize that none of the previous constructions satisfies all these four conditions, which motivated us to find explicit epsilon extreme depth robust graphs with low in degree, which are also locally navigable. Why do we care about the explicitness of the graph? When it comes to cryptographic applications, security comes from the assumption that the graph is ED depth robust. Randomized constructions are ED depth robust with high probability, but not with 100% certainty. If the graph designer is honest, then the sampled graph will be depth robust with high probability. But what if a malicious party bribes the graph designer to pick a non-depth robust graph? Would we even notice? Unfortunately, the answer is not necessarily. Previous works have shown that testing depth robustness is computationally intractable, even approximately. So we give the first explicit constructions of epsilon extreme depth robust graph with in-degree order of log n, which are locally navigable. And if we apply the in-degree reduction gadget from ABP17, then we get a constant in-degree graph as shown here. You could get into the details in the full talk at the conference or by checking out our paper. Thank you, and see you then.